This page introduces the topic, HPLC for practicing scientists, specifically focusing on reversed phase mobile phases and their fundamentals and selection. It's part of the Learning HPLC with Michael Dong series. This slide defines the mobile phase, MP, as the solvent carrying solutes through the column. In HPLC, the MP is crucial as it controls the separation by determining the solute retention factor K and selectivity A. This slide explains the concept of mobile phase A and B, MPA and MPB, where blending two solvents controls retention. A binary MP is generally used in RPC. Mobile phase A, MPA, is the weak MP and is always an aqueous solution. Water is a weak solvent in RPC. Mobile phase B, MPB, is the strong MP and organic solvent, e.g., ACN or MeOH. This slide outlines the general requirements for HPLC solvents. These include good solubility of sample components, being non-corrosive, high purity, low cost, UV transparency, low viscosity and toxicity, and non-flammability. This slide presents a table of common HPLC solvents and their attributes. The table includes solvent strength, EO, boiling point, BP, viscosity, UV cutoff, and refractive index for solvents like tetrahydrofuran, THF, acetonitrile, ACN, 2-propanol, methanol, MeOH, and water. It also notes the relative viscosity of ACN, MeOH, and water. This slide focuses on the strong solvents in RPC, the MPB. Common MPB choices are ACN, MeOH, and THF. ACN is preferred due to its low viscosity and UV transparency. MeOH offers different selectivity and can hydrogen bond with analyte molecules. THF has high solubilizing power but is toxic and used in GPC. This slide discusses the weak solvent in RPC, MPA. MPA is typically water, often with acidic additives like formic acid, Fa, acetic acid, AA, or trifluoroacetic acid, TFA, at 0.05 to 0.1% to suppress ionization of residual silanols and improve peak shapes for basic drugs. High pH MPA can be used for basic analytes. This slide continues the discussion on the weak solvent in RPC, MPA. It explains that buffers are used for critical methods to stabilize pH, typically using phosphate, formate, acetate, or bicarbonate. Volatile additives are needed for LC/MS applications, creating MS-compatible methods, such as using 20 mm ammonium formate at pH 3.8. This slide provides a table of common RPC MPA additives and buffers, including their pKa values and UV cutoff. The table includes trifluoroacetic acid, TFA, difluoroacetic acid, DFA, phosphate, formate, Fa, acetate, carbonate, and ammonia. This slide illustrates the effect of % MPB on TR in RPC using the linear solvent strength theory. It shows that log K is inversely proportional to % MPB, demonstrating the relationship between solvent strength and retention. This slide discusses the effect of solvent type on selectivity, RS, highlighting the differences between MeOH, ACN, and THF as proton donors and acceptors. Changing selectivity is an effective way to separate critical pairs, where increasing it from 1.1 to 1.2 can double RS. This slide summarizes the key points: the fundamentals and rationales for RPC MP selection, the dependence of retention on lipophilicity and MP strength, the role of acidified water as MPA, the preference for acetonitrile as MPB, and the importance of selectivity in separating close-eluting analytes. This slide lists references for further reading, including Introduction to Modern Liquid Chromatography and HPLC and UHPLC for Practicing Scientists.